Section 10.3, chi-square independence test. So we're going to do a new test in this section where we're testing for independence between two variables. It's very similar to the goodness of fit test from the previous section, just some small differences which I'll show you as we go through the example. But first, since this is a test of independence, we need a kind of reminder of a couple rules from Chapter 5 where we introduce independence. So the first was the kind of definition formula. If A and B are independent, then knowing that one has happened doesn't affect the chance that the other one has happened. And the way that came out in the formula is that the probability of A given B would be the same as the probability of A without the given of B. So that the idea there is whether you know B has happened or not, the probability of A is the same. Then we had another rule, the special multiplication rule, that said if you know things are independent, then the probability of A and B would be the probability of A times the probability of B. And this rule is good for reminding us of what independence means, that if B has no effect, then they're independent. But this is actually the rule right here that we're going to use as we do the hypothesis test. So I'll kind of box that one as the more important reminder. So let's go ahead and jump in and just look at an example, and we're going to kind of try and follow the philosophy of section 10.2. And if things change, I'll just point out those differences as we go through the problem. So the following table cross-classifies a random sample of 513 Americans by using their education level and their smoking habits. This is sample data that's based on a 2011 CDC study. And they want us to know, does the data provide sufficient evidence at the 5% significance level to show that the smoking status is dependent on education level? So the first thing that we have to decide is looking at that statement, starting right here and ending right there. So smoking status is dependent on education level. That statement is either H0 or H1, and we have to decide which we think it is. And the rule that we've used so far has always been for HO, you have to have equality. And in the last section we read phrases like is the same as and is different from. And it was easy to say is the same as is like equals and is different from is like a does not equals. But if you have dependent, the other alternative is independent, trying to decide which of those sounds like equals is not obvious. But if you come back here and look at these formulas from Chapter 5, if they're independent, these things are equal. If they're A and B are independent, these two sides are equal. If A and B are dependent, these are not equal. And if A and B are dependent, these are not equal. So when you think about the formulas, these formulas hold equals when things are independent, but they are not equal to each other when there's dependence. So that formula gives us that connection where saying independent is like saying equals for these formulas, and saying dependent is like saying does not equal. So since it's independent that creates equality, the dependent is the not equals to type of word, and that's going to go in H1. So I'm going to say H1 is that smoking status is dependent on their education level. And then we need the equality idea in H0, and that would be independent of. So smoking status is independent of their level of education. Alright, so that may seem a little bit tricky because it doesn't sound exactly like an equals. You have to chase it through the formulas. But the good news is that's going to be true every time we do a test of independence. We'll always put independent of in the H0 statement and always put dependent on in the H1 statement because independence always goes with equality. That's not just for this example. And then step 2 would be to decide on a significance level, and it says here to do this test at the 5% significance level. So I would say that alpha is equal to 0.05. And then we're going to want to move on to step 3 and calculate our test statistic. And it turns out we're going to have the same test statistic in this section as we did in the last one, where we're doing O minus E squared over E for several different categories. And so we just need to see that there's a difference in the expected frequency. So I want to show you that, and then we'll get to the main work of the test statistic. So just like a goodness of fit test, only we compute our expected frequencies using the assumption of innocence, or the idea that HO is true, which would mean that these are independent events, and therefore the probability of A and B is equal to the probability of A times the probability of B, which is this box formula here that only holds true if A and B are independent of each other. Alright, so let's see what that would look like for the square expected frequency, or the expected frequency for the square no diploma and smoking. So no diploma and smoking is the overlap between the no high school diploma row and the smoking column. So let's go ahead and take a look at that. That would be this square right here with the 20 in it. That's the overlap of no high school diploma and smoking. So we want the expected frequency for that. And if we were still in section 10.2, we'd say the expected frequency was n times p, or maybe pi, where the p was the probability that would hold true for that category if HO was true. And so I'm going to just translate that as probability for now. So that would be the probability of no diploma and they smoke. And then next, I would think about if HO is true, what would this probability be? And if HO is true, that would mean we have independence. And if we have independence, then an AND could be turned into a multiplication of the two individual pieces. So now I'm going to say that E is equal to N times the probability of just the first piece, no diploma, times the probability of the second piece, which would be that we have a smoker. And it's important to point out that right here, that equal sign is only true if HO is true. Because we can only break this AND into a multiplication if we know we have independent events. And if HO is true, that would be the case. And that may seem weird, well, how do we do that if we don't know if they're independent or not yet? But remember, this is the frequency we would expect to get if HO is true. So when we're calculating that, we're making the assumption HO is true. We'll then later compare that to what we observed and see if that assumption seems to hold up. So now I want to fill in the different values here. And I can fill in the value of N. Our sample size, we can look back up here, was 513. And then I want to fill in the probability of someone not having a high school diploma. And here's where I get into a little bit of trouble. I don't know the true probability in the population that somebody would have no high school diploma, so I'm going to have to guess at that. And my best guess would be from the sample. So in the sample, we had 72 people with no high school diploma out of 513. So if I put that as the fraction for that probability, 72 out of 513, that's just from a sample, so it's only a guess, but it's the best guess I have. Because I'm guessing there, I'm going to change this to an approximately equal, but that's not actually something I would worry about you doing in your test, and you'll see why as we kind of move on with this problem. The probability of a smoker, same idea. I don't know what that answer is in the population, but I can estimate it from the table. If I come up to the table, we had 107 smokers altogether out of 513 people. So my estimate that a randomly selected person would be a smoker based on this sample would be 107 out of 513. And then I'm going to go to the calculator on that, but before I do that, I notice a little math I could do by hand. This 513 out front could cancel one of the 513s down here. And so I end up with just 72 times 107 over 513. And at that point, I'll go ahead and go to the calculator. So 72 times 107 over 513, no parentheses necessary. Just multiply those two together, divide by 513, and we get 15.02. It's pretty standard to round expected frequencies to 2 decimal places, so I'm going to go ahead and just follow that rule. So 15.02 for what I expect for that square. So I could even plug that in. We'll kind of finish this off on the next page, but what we typically do is put our expected frequency right underneath the observed frequency, and then we also tend to put it in parentheses, just a few things to help us differentiate. So the observed frequency is what we saw in our sample, and then we just calculated what we would expect to see if HO is true. And then just like we did in the previous section, we're going to do O minus E squared over E to decide if that difference is a big deal or not. But here's the key thing to realize. We're going to do that for that square, but we're going to do it for this one, this one, this one, this one, this one, this one, and this one. Every time we have a smoking category intersecting an education category, we're going to look at the O and compare it to the E for that square. So if you think about what that means, It means I have to go through this process 7 more times for those other squares that I need to get values of e for. And it's kind of a long process, so it'd be nice if we could speed that up a little. So we want to look to see if there's any pattern there that could help us find a shortcut. So if you look at the 72 and the 107, and then you go back to the square we were working on, 72 was the row total for that square, and 107 was the column total for that column, or the column total for that cell or square. So when you're working on a square trying to get your expected frequency, or at least for this one, what we ended up with was the row total 72 times the column total 107 divided by the sample size of 513. And it turns out that's not just a coincidence for this particular cell. That happens every time you're doing an expected frequency. So instead of doing all this work each time, a shortcut that we could do is for each expected frequency we need, we can just take r times c over n, where r is the row total and c is the column total for the square or cell that you're working on at the moment. So we're going to go ahead and turn the page and do those expected frequencies for all the rest of the squares. So continuing on with this example, we're going to go ahead and use that shortcut formula of E equals R times C over N to fill in the missing expected frequencies. The 15.02 that we just calculated on the previous page, I went ahead and copied over into this grid, and I've already pre-done a few of the others for us to save a little bit of time, but we still have some to fill in. So let's go ahead and start working on those. If I want to do this square right here for they don't smoke and they have no high school diploma, then let me bring the calculator in and see how that would work. I want to take the row total for this square, which is 72, times the column total for this square, which is 406, and divide it by the sample size, which is 513, and that would be my expected frequency, so 56.98. And then I want to do that for this cell or square where they have high school only and they're a smoker. So for that square the row total is 221, and for that square the column total is 107, so I multiply those together, divide by the sample size of 513, and I get 46.10. And then dropping down to this cell, trying to do the same thing for those that have some college and don't smoke. For this square right here, the row total is 117, column total is 406, divided by 513, gives an expected frequency of 92.60. And then just one left. We want the bachelor's degree or higher and they're a smoker. And so for that cell, the row total is 103, the column total is 107. So I'll multiply those together and divide by the sample size of 513, and I get an expected frequency of 2148. Alright, so let's go ahead and get back to work on our main hypothesis test. So at this point we have 8 observed frequencies, and now we've got 8 expected frequencies. Our test statistic is just like the last section. It's the sum of the O minus E squared over E for all of the different category combinations. And each O minus E squared over E is like a mini test statistic for us. And so what we want to do is fill in the ones that are missing, add them all up, and that sum would be our overall test statistic. So I've done, it looks like, 5 of them for you, and 3 are left to do. And the way you can tell which ones I've done and which ones I haven't is that I've laid out my mini test statistics in the same pattern as the table. So this 0.435 is upper right hand corner of what I've written, so it should be upper right hand corner of the table. This 1.911 is lower right of what I've written, so it should be lower right cell in the table. So this first blank is upper left, so that should be this square that we started out talking about, with an observed frequency of 20 and an expected of 15.02. And I'll think about it just intuitively at first. If I was expecting 15 people at a party and 20 showed up, is that a big deal? That's about 33% more than I expected. That seems kind of borderline to me. Like, if I'm expecting 15 and 20 show up, I'm not sure if I'm going to have quite enough food to cover all of that. But let's look at it as a mini test statistic and see, or kind of a mini z-score, and see what it looks like to the math. So I would take the O of 20, subtract the expected of 15.02, square of that, and then divide by the expected of 15.02. And I said I kind of wasn't sure, like if I'd have enough food to cover them. Well, if we asked the formula, is that unusual? I get a 1.651, which I'll fill in right here. And that comes across as, well, kind of unusual, but not quite, right? Like it's in the gray area. It's not normal because it's not smaller than 1. It's not quite unusual because it's not bigger than 2. So that kind of really honestly matched with my confusion a little bit. Let's see, what's our next one? Second row, column 2. So that should be this square right here. So I would do O, 168, minus E, 174.9. Square that and divide by E, 174.9. And just a quick thought about it, if I invited 175 people to a party, or I was expecting 175 people, and I got 168, that actually feels pretty close to me. So that means I expect a small mini z-score and only get 0.272. So that matches up with my intuition. And then we need the bottom left, and looking at the chart, the bottom left is an O of 9 and expected value of 90 or 21.48. If I was expecting 21, 22 people to come to my party and only 9 people showed up, I would be a little sad. That feels like a very big difference to me. So let's look at that on the calculator, but I expect a big mini z-score from that one. So the O of 9 minus the expected of 21.48, square that and divide by the expected of 21.48. I thought that felt like a big difference just on an intuitive level. Mini z-score 7.251. Alright, so now we want to add all of that up to get our test statistic. So we want to look at all of these numbers in this chart and see what the total comes out to be. So just typing those in, adding them all up real quick. So I get a total of 12.572. So that's going to be my test statistic. And next I want to decide, is that a big enough value for the test statistic to reject HO, or is it small enough that it could just be random variation and therefore it's plausible that HO is true and I won't reject it. So to decide that, I want to calculate a p-value, and to do that I need to do a DF, or know the DF. And when you look at this table, let me get the calculator out of the way here. When you look at this table and you look at what we did with this with 8 categories and 8 mini z-scores, you'd probably expect the DF to be 7, because in the previous section it was the number of categories minus 1. So it turns out that that's not the case here. Our formula for the degrees of freedom is R minus 1 times C minus 1, where R is the number of row categories and C is the number of column categories. So our degree of freedom on this, actually we would say, how many row categories do we have? 1, 2, 3, 4 rows. So we would do 4 minus 1, times how many different column categories do we have? Smoking and not smoking. We don't count the total as a category. So smoking or not smoking are our categories vertically. So that would be a 2 minus 1 right here. So we end up with 3 times 1, or just a DF of 3. So that's a little different than what you're expecting, but these degrees of free formulas are on the formula sheet. So I would just advise that when you're working on the homework, and especially when you're taking a test, that if you forget the DF, you look it up there. So just a kind of quick mention about why the DF is 3 here. One of the things that I always do when I'm doing my expected frequencies is I try and look at those last digits to see if they add up to a whole number. 0, 2, and 9, 8 add up to a whole number. 10 and 90 add up to 1. 40 and 60 add up to a 1. 0.48 and 0.52 add up to 1. And the reason that I can check that is the values of O have to add up to 72, but the values of E also have to add up to 72. And so if you think about it, if you already know the total, then once you know one, you know what the other one has to be. And so there's an argument to be made that there's only flexibility in this chart, or there's only a degree of freedom for 3 of these squares, which would be these 3 right here. It really could be any 3, but these 3 are the easiest ones to think about. If these 2 expected frequencies have to add up to 72, then once I know that this O was 20 and this expected was 15.02, that means I observed about 5 more than I expected. Then over here I have to observe about 5 less than I expected. It has to balance. So there's really no freedom in how this turns out. This one could almost be whatever, but then this one becomes locked in. And the same thing is true here. When you know what the difference is here, you know the difference here. When you know the difference in this one, you know the difference here. And then why don't I go down and contain the last one in the red as well? That's because by the time I know these three, this one is locked in as well, because the addition has to work vertically too. If the O's add up to 107, the expecteds have to add up to 107. So once I know what these three are, I know what this one has to be. So there's an argument to be made that only 3 of these square have a degree of freedom as to how they're going to turn out, and then the other 5 are locked in after that. And that's kind of where the phrase degrees of freedom comes from. How much of your information is truly flexible or free to change, and how much of the rest of it is just locked in based on what's happened with other stuff. So it is a confusing topic. You don't have to memorize what I showed you there. Again, these degrees of freedom formulas are on your formula sheet, but I just wanted to give you a little bit of an explanation for where that phrase comes from. It has to do with how much of your data has the ability to truly change and how much of it is locked in based on the other. So 3 squares have some degree of freedom to which they can be different things, and the other 5 then just get locked in. And you could say it's not total freedom because this expected frequency could not be 83 when the total was 72. So that's where that phrase comes from. All right, now let's get back to doing the math. If we have a test statistic of 12.572 and we have 3 degrees of freedom, could that amount of differences just be random variation, or is it too much for random variation and we should reject HO? So I'm going to draw a chi-squared curve, which is going to have that right skewed look to it. If I drop down from the peak and move a little bit to the right, that would be my DF of 3. So then I would think about, where does my test statistic of 12 fit in? Remember, this is 0, so 3, 6, 9, 12 is about over here. I don't like to put values off the picture, so I'll just show it right about here. But anytime your test statistic is basically off the picture, it means that your area and therefore your p-value is going to be small. So I'll try and shade this in red. It's not going to show up, I don't think. And that kind of makes sense that it doesn't show up, because I think the amount of area is too small for us to see, and we'll verify that with the calculator. Tests of independence, like the goodness of fit tests, are always right-tailed, so the p-value is going to be the area to the right of that test statistic. So I'd get that by doing chi-squared CDF from 12.572 to infinity with 3 degrees of freedom. And going to the calculator, I can get an approximation for that p-value. So I want to go to the distribution menu, choose chi-squared CDF, left boundary 12.572, right boundary is infinity, and we have 3 degrees of freedom. I expect a very small answer, and I get a very small answer, 0.00, let's see, 56, but followed by a 5, so 57. So that's going to be my p-value for this problem. To be honest with you, I almost expected an E negative something because we're so far to the right, but with a right skewed distribution you might get a little bit more area than you were expecting sometimes. Alright, so let's go ahead and think about finishing this off. On all hypothesis tests, it's kind of the goal of the work to see if we can gather enough evidence to reject HO, so we're kind of hoping in some sense to reject HO, and so I want to reject HO in step 5, but this says if I do, the risk of making a type 1 error is 0.0057, and I said that like I wasn't going to do it, right? But if I do, but I actually am going to go ahead and take that, because a 0.57% risk is much smaller than the 5% risk that we said we were okay with. When our p-value is small, it means the risk of a type 1 error is low. We take the risk by rejecting HO. So I'm going to go ahead and reject HO on this one and say I did that because it was an acceptable risk of a type 1 error. And even though I'm talking about that as risk, the other thing that we could say is, look, we saw some differences in the table, and that could mean that things are dependent on each other, these 2 variables, but it could also be that the 2 variables are actually independent and those differences were just due to random variation. but the p-value says the chance of those differences being just due to random variation is low, about 9-10 times lower in a sense than it could have been. We could multiply this by 9 and I think still end up underneath our p-value. Let me test that. Now that I've said it, I'm a little nervous about it. It turns out 9 times would put us just over, but we could be about 8 times bigger and it would still be an acceptable risk. So this is a low risk situation, low enough for us to reject HO, and it's a low enough chance that it's random variation that we feel random variation is not the plausible explanation, so we're going to reject that it was random and go with the alternative. And the alternative was H1, that said that smoking status is dependent on their education level. So when I write that out, I'm going to say there is enough evidence at the 5% significance level to show that smoking status is dependent on the education level. And again, my evidence comes from my test statistic and seeing that the chance of that test statistic being just due to random variation is very low. So it's not plausible that these things are independent and I got these differences due to random variation. It makes more sense to say these differences are so big that they indicate that there is a dependence between our variables, and our variables are smoking status and education level. All right, so that's the first complete first complete test of independence that we're going to do. And the steps and requirements are very similar to goodness of fit. So I didn't list them here on this handout, but they are in the book in section 10.3, so you can take a look. The only real difference is how we compute our expected frequency. We end up using this shortcut formula, R times C over N. And then the other one is the DF, which is no longer K minus 1, but now it's R minus 1 times C minus 1. And again, I think that difference in DF is easy to forget or mix up, so I would suggest looking at your formula sheet when you do a DF for a chi-squared test. By the way, just a quick comment about the requirements. The requirements are the same as before, which means you need all of your expected frequencies to be bigger than 5. And our expected frequencies are 15, 56, 46, 174, 24, 92, 21, 81. They're all bigger than 5, so we're fine on the requirements. And finally, looking at Part B, based on the results of this test, which educational level appear to be most likely to smoke? Explain. So I always thought it was interesting that I would see problems that would talk about whether two variables were independent or dependent, and it would end up saying they were dependent but not talking about the relationship. So we see here that smoking status is dependent on the educational level, but what's the case? Is more education lead to more smoking, or does more education lead to less smoking? So to answer that question, we just do something rather simple, just some basic math here. We're going to add a new column and call that the percent of smokers, and just figure that out for each one of these groups. And that's fairly just straightforward arithmetic to answer that question. So what percentage of the people with no high school diploma are smokers? Well, there were 20 smokers out of 72 people. So that's 0.2778 or 27.78%. What percent of those with high school diploma only are smokers? Same math there. There are 53 smokers out of 221. So that ends up being about 23.98%. For some college, we had 25 smokers out of 117 people, which is 21.37%. And for people with a bachelor's degree or higher, we had 9 smokers out of 103, and so that turns out to be about 8.74%. So in terms of the answer to that question, which of those education groups seems to be the most likely to smoke? That seems to be those who have no high school diploma at 27%. And they didn't ask, but which group is least likely to smoke? Those with a bachelor's degree or higher. So based on the results of this test, which education level appears to be most likely to smoke? It seems to be the least educated, or those with no high school diploma. So I think a reasonable question to ask at the end of this is, does getting more education cause people to stop smoking? And we don't actually know that. We're saying here these things are connected, but we don't know if it's a cause and effect or not. That is something that would be worth investigating, but this test doesn't show whether you have a cause and effect. It just shows whether there's a connection. And so it does seem, based on our results, that there is a connection between those two, that there is a relationship between whether someone smokes or not and how much education they have. But we don't know if that's cause and effect, and even if it is, we don't know what direction that cause and effect goes. So that is an important thing to know about these. Even when you do find that there's dependence, cause and effect is still uncertain. All right, that's our only example for section 10.3. There are more examples available in the book if you feel like you need another one to feel comfortable with this.